Hello all. The project which we have undertaken for our third year design project is mechanically operated Ambu ventilator. Our group consists of myself Matthew Jeligan, project manager, Nikhil P. Charian, assistant project manager, Leon Vincent, and Srinath PS. Our project is guided by engineer Arun K. Varghese of Mechanical Engineering Department. Introduction. Due to the current COVID-19 pandemic, a surge is witnessed in demand for mechanical ventilators for treating patients. Due to increased demand, there's a shortage of ventilators. So our aim with this project is to develop a low-cost mechanical ventilator at a fraction of the cost of the current ventilator that is currently used in the market. We are planning to employ new and alternative manufacturing techniques like 3D printing so as to develop the product. The project is divided into three stages. Stage 1 consists of ideation, design constraints, data collection, preliminary design, and reference. Stage 2 consists of design improvisation, component selection, cost analysis, mathematical calculation, and Arduino code. Stage 3 consists of finalization of design, prototyping and manufacturing, assembly, and conclusion. Stage 1 Ideation. Ambivag is a device which is already being employed by medical practitioners for artificial respiration in emergency case. The only problem is that for continuous pumping of air to the patient, it cannot be sustained for long hours. Design constraints. The proper synchronization of rate of air being pumped and volume control is tough to achieve. Cost of various flow sensors and various sensors, flow measuring devices, etc. are very high. It should be light and compact. Data collection. The slide shows the various medium through which we have collected data. Because we are making such a sensitive device, we made the effort to also collect data from medical practitioners. We got to know that three types of Ambu is usually employed for patients according to their age group. For infants, 250 ml volume Ambu is used. For children, 500 ml volume Ambu is used. For adults, 2600 ml volume Ambu is used. Also, an Ambu is approximately squeezed 8 to 9 times per minute, and after each actuation, the Ambu and after each actuation there is a gap of 5 to 6 seconds. The oxygen saturation and pulse of the patient is measured using pulse oximeter, and the normal saturation level of oxygen in a patient is between 90% to 100%. Preliminary design. The proposed system consists of a mechanically operated ambu in which the ambu is actuated by a rack in pinion or slider crank mechanism. The rate of volume control and discharge is controlled using potentiometers. The system will also have a fail-safe logic so that the pressure will not build up in the system and harm the user. Moreover, the system ensures that proper distancing can be maintained with the patient and the operator, which is essential in the current circumstance. These are the various these are the links to various sites we had used for research and reference purpose. Stage 2: Design Improvisation. Improved design has drastic changes to the initial design. The rack and pinion mechanism has been replaced by simple gear train mechanism with a pair of arms. The main aim of changing the design was to mimic the exact action of pressing of ambu bag while using the hands itself. In this figure, attention has been given to small details as we have incorporated electronic circuit box which houses all the electronic parts, and also we have given an LCD display to display the various parameters. Also, in this design we have used a stepper motor, naming namely stepper motor is NEMA 23. Next slide is component selection and cost analysis. From the cost analysis, we came to know that the project will approximately cost us around 16,500 once it is fully completed. The mathematical calculation and Arduino coding is displayed in the current slide. The maximum volume output per stroke of our device is 622.8 centimeter cube volume of air. This is the Arduino code. The main manufacturing technique used is 3D printing. 3D printing or additive manufacturing is the construction of a three-dimensional object from a CAD model or a digital 3D model. The term 3D printing can refer to a variety of processes in which material is deposited, joined, or solidified under computer control to create a three-dimensional object. Beneath, you can see a PLA roll, which is the material through which our project was 3D printed. The full form of PLA is polyacetic acid. It is a vegetable-based plastic material. It is fully biodegradable and it is a thermosetting polymer. PLA has good geometrical stability, so it is suitable for manufacturing process. PLA is used for rapid prototyping, and the main application of this metal are in making toy, figurines, non-functional prototypes, etc. PLA usually comes in the form of a wire on a spool, which is fed to the extruder head where the plastic is melted and deposited into fine drops on the printing tray. The material is translucent in its natural form, but spools of dyed filament can be used to make objects in different color. We had used a dyed filament, and the filament color was black. The slide shows the 3D printed parts. The slide depicts a print failure. Usually, a 3D print failure occurs when there is a disruption of power or if there is an error in the design phase. In our case, the power got disrupted, so the print failed. The figure shows a servo motor horn. This horn was specifically designed in lathe so that our servo motor can mate with our gear system. These are the various attachments of the Ambu bag. This was an assembling video done in SolidWorks. This is our final outcome. Working. The mechanical operated ambubag ventilator consists of an ambubag which is actuated by a pair of arms connected to a servo motor S8218. The servo motor has a peak torque of 40 kg/cm at 7 volt. That is specifically why we had changed from stepper motor to servo motor. In our improved design, I had already mentioned that we have used a stepper motor. But while we use the stepper motor, we couldn't produce enough torque to effectively press the bag. So we changed it to servo motor. The servo motor drives a simple gear train in order to actuate the bag. The servo motor is connected to the gear train via a metallic horn which was specifically designed to mate with the gear train. The brain of the device is an Arduino Uno R3 to which the various logics and parameters of the device are coded. It also has a pulse oximeter to identify the pulse and oxygen saturation level of the patient. The various parameters are displayed on an LCD screen fitted to the body of the ventilator. Our current design requires the ambibag to be changed according to the age group of the patients. This is done in view of the safety of the patient using it. The ambibag we have used has a total volume of 2600 ml. Per stroke, the output volume is approximately 620 ml of oxygen. Each actuation is followed by a 5-second gap. In a minute, the bag is therefore pressed 8 to 9 times. Our system can work directly on current, and if the situation demands, it has also got a 12-volt 7Ah lead acid battery to be used in case of power failure. If a power failure is detected, the system automatically switches to power from the battery. Hence, the operation of the device is not compromised. This is a working video of our project. You can see that the patient is holding a sensor in his hand. That sensor is the pulse oximeter. From the pulse oximeter, the display from the pulse oximeter, details are fed into the Arduino, from which it is displayed to the LCD screen on the device. You can see the O2 saturation level and BPM being displayed. Conclusion: COVID-19 pandemic has got every one of us unaware, and the need for emergency tool and protocol for life-saving ventilators is essential. Our product can be used for providing artificial respiration to COVID patients, and it also can be employed in ambulances to provide respiration in accident case also. The basic function and operation of our device is highly satisfactory, but with that said, we have limitations also. In advanced ventilators, parameters like tidal volume, IE ratio, continuous mandatory ventilation (CMV), volume control ventilation (VCV) are measured. But our current system does not have that capability. The addition of the above mentioned parameters is a Herculean task, but because we have to add various flow measuring device and sensors whose procurement is currently difficult in the current situation. But we are confident with that. But we are confident that with some slight modification, we can include these parameters as the basic working mechanism of our system is at par with the current most advanced ventilators. Thank you.